Hi, welcome to the second part of this series. In the first part, we installed Rust, created our first project, and added a simple status endpoint using Actix. In this video, we'll handle the app configuration, set up our database connection, and create our models for the TODO service. It is a good practice to separate the configuration from the code. Right now, we have a couple of hardcode variables, like the host and the port of the server. Those variables may be different depending on the environment on which we will deploy, and we don't want to have to compile the application each time we need to change a configuration. One way to do it is to get the configuration from the environment variables. To do so, we'll add two new dependencies to the project, .m that we will use to read the configuration from a file and load it into the environment variables, and config that can read configuration from different sources and load it into a type that we can define. Next, we will create a new file, config, that will contain the code to load the configuration from the environment variables. We will create a public struct config that will include all the configuration for the app and another struct for the configuration specific to the server, like the host and the port. Then we can include that into the config struct like a hierarchy. Next, we will create a function that will load the configuration from the environment into the struct we just created. So let's implement a factory for the config. This static method will return a result. A result is used for error handling. It is an enum that has a value OK in case of success, an error in case there is an expected error. The success case will be the config itself, and the expected error will be a config error from the config library. So let's import config error and use cerdy so we can deserialize our config structs. The same process we did with the status struct. Then, in our method, we need to get a new instance of the config struct from the config library. We can think of this struct as a repository or an aggregator in which we can merge multiple configuration sources. In this case, we only want to get them from the environment variables. Once we have that, we can try to convert the configuration into an instance of our config struct. We do exactly that with the try_into method, and that should be all. Now, on the main file, we need to do two things. First, since environment variables are not that convenient while we are developing, we will use .m to get the configuration from a .m file and load them into the environment, just like this. So let's create the .m file in the root of the project. The configuration will be the uppercase name of the attributes following the hierarchy we defined, so server.host and server.port. Next, we can get an instance of the configuration by calling the front-end method we just defined and unwrap to get the value from the result. Once we have the config, we can access the server host and port just like this. We make sure to replace every instance. We can check that everything looks good with cargo check, and then cargo run to compile and run the application. Perfect. Now let's set up the database. In this case, I want to use Postgres, and I find it convenient to use Docker and Docker Compose for this type of services while I'm developing, since containers are easy to set up and discard when you are done. So let's create a Docker Compose file. Define the spec version as 3.1 in this case. Other versions should be similar. And in the services, we'll have just Postgres for now. Then as an image, I will use the Alpine version of Postgres 11 to save a bit of storage space. Then the restart policy would be always, and we need to define a couple of environment variables for the password, the user, and the database schema. And finally, we'll expose the default port for Postgres. Now, to run the database service, we use docker compose app and -d to make it run in the background. And the service is running. I already have a Postgres CLI installed, so I can connect like this. Just specify the host, import user and database. Oh, the user parameters should be uppercase, and we put the password, which is Actix as well. Cool, we are connected and have a brand new and empty database. Now, to make it quick, let's create our database DDL in a new SQL file. Create a table for the actual to-do list. We choose an auto-incremented ID as a primary key and a title. Then another table for the to-do item, also with its ID and title. A column to set it as checked with the type boolean and default value false. And a foreign key to the ID of the list. Let's also insert a couple of values as test data, list 1 and 2, and also a couple of to-do items. Then we can add a couple of drop if exists statements at the beginning, so we are able to run this script as many times as needed. Great. Now let's use the CLI again to create our database. And looks like I make a mistake. It should be a parenthesis instead of the curly brackets. So I'll fix that and try again. Good. I will connect to take a look. The relations are there. Now let's try with a query to see the data. Perfect. Now we can add the configuration for Postgres in the .m file. So I will write pg for Postgres as namespace and start defining the user, password, host, port, and DB name. And an extra namespace for the connection pool configuration. We just need to set the max size of that pool. So let's define the values. For the max size, I will use 30 for now. Next, we will need to add a couple more dependencies. Let me explain what this is. TODO is an event-driven, non-blocking platform to write asynchronous applications in Rust. Actix uses TODO event loop for the actor system. Now, TODO PG mapper and TODO PG mapper derive are just a bunch of traits and macros to facilitate the mapping from Postgres tables to structs. Deadpool Postgres is a dead simple connection pool for Postgres, and TODO Postgres is a native asynchronous client for Postgres. Okay, now let's include the Postgres database connection in our struct. We'll add a new attribute pg with the config struct provided by the Deadpool Postgres library. The database configuration we added previously will be loaded into this attribute. With this, we should now be able to create a connection pool. Back in the main file, let's declare a variable for the pool and get the Postgres configuration from the config variable. We'll need to import a type to specify that we don't need a TLS or SSL connection for now. And we can call create pool directly from the connection pool configuration. We need to use wrap to get the pool in case of success. Then we want to make this pool available for the request handlers in the app. We can do that by using the application data. Since in Rust the variables are in charge of freeing their own resources, resources can only have one owner. To move the ownership of the variables to the closure where we created the app, we use the keyword move. The HTTP server constructs the application instance for each thread. Thus, the application data must be constructed multiple times. Now, we can define the application data like this and specify the reference of the connection pool. We make a copy of the reference by using clone. Cool. Now, let's define the structs for our database tables in the models file. We need one public struct for the to-do list with an ID as integer 32 and a title as a string, and another struct for the to-do item, also with the ID and title, and a checked attribute as boolean. Lastly, the list ID. Now let's add a couple of imports for the serialize and Postgres mapper. We copy the derive macro from status, and besides serialize, we also want the code to deserialize, and the Postgres mapper will help us map from Postgres table. We also need another macro for the PG mapper to specify the name of the table, and we just do the same for the to-do item. Now again, to organize, let's create a handle file and move the status handler there, and we also need to add the module reference in the main file. Okay, we add the required imports to the file and make this function public. Finally, we import all handlers into the main file. Now let's quickly check that everything works fine. Good. Now let's create another file to include the code to query the database. I will create the function to get the to-do list. We will import the models and use the Deadpool Postgres client. It will receive a client as a reference and will return a result with a list or a vector of results, or an error in case of failure. We will create a prepare statement using the client reference, call prepare, and pass the query to get all the to-do items. We await for that and unwrap the result. Now, let's declare a variable to hold the to-do's result. Use the client to run the query. We pass the reference of the prepare statement and a reference to the list of parameters. Since there are no parameters, just a reference to an empty list. Await for it, and let's use expect to define a custom error message. Now we receive a list of rows as result, but we want to use our model struct. For that, we can use an iterator and map each row to the to-do list. And to convert it from the row, we just need to import a trait from Tokyo PG mapper called from Tokyo Postgres row. This will enable us to use a static function from row ref that will do that conversion for us. We pass the row and unwrap to get the value. Then we can collect the result into a vector of to-do lists. To make it simple, we can just return the vector directly inside the OK-enum. Next, we can create the handler, again, to get the to-do function. But this time, we receive the database connection pool. To tell Actix to extract the connection pool from the application data, we use web data and specify the pool type in the generics. So let's import pool and also client. And this handler returns a response. Now we need a client so we can use the method from the DB module. And we can get one from the DB pool by calling get. We await on that and specify an error message with expect. Now that we have the client, let's define a variable to store the result of the query. Import the DB module, and now we can call getToDo, pass the reference of the client, and await. We can use match to get a response based on the result. So in this case, if everything is okay and we got the to-dos, we can create an HTTP response OK and have the to-do list as JSON. In case of an error, we return an internal server error and call into to make it a responder. Now we are almost ready. Back to the main file, let's include the module DB and add the new route for the to-do. To also make it match the trailing slash, I find it easier to add this regex to the end of the path. Next, define the get handler that will be the function getToDos. We save and run the server again. Good. Now let's try it with a curl. It works. Let's print it with a better format. Great. We can see the to-do list. And that will be all for this video. In the next video, we'll do a small performance test and add the handlers to create the to-do list, get the items, and mark a to-do item as checked. Do you find this framework easy to use so far? Please let me know in the comments. If you liked the video, hit the like button. Don't forget to subscribe for future videos. Thanks for watching.